Hello, everybody. In this lecture, I will quickly go over the different measures we have to quantify how well a classification algorithm performs. A point of reference is the ISLR book, page 145, where it talks about the confusion matrix, sensitivity, specificity, and later area under the curve, true negative, false negative, what is a false positive rate, true positive rate, type 1 error, etc. powers. So it's coming from there. Now, in its simplest case, a classification is binary. You have positive or negative, or you have 1 and 0. You have a true response, and you have a predicted response. And now the question is, how do you measure how well the predicted response is doing in comparison to the true response? Now, one measure is a false positive rate, which is also known as a type 1 error, and it's 1 minus the specificity. So what is a false positive rate? It's the number of false positives divided by the negatives. So what is a false positive? A false positive is when y hat is positive, when yi is negative, or when yi hat is 1, when yi is truly 0. That's a false positive. Now, what is a negative? What are the number of negative? Is it about the predicted responses or the true responses? And this is a subtle point here to remember. When you calculate the false positive rate, the number of negatives is the number of negatives in the true response. So then what is specificity? Specificity is the true negatives divided by the negatives. So essentially, I don't know. There is no other way for me to express it. It's a true negatives. True negatives meaning that how many of the predicted responses that are predicted as 0 are actually 0. Then we have the type 2 error, which is a false positive divided by the positives. And positive here is, again, the positives in the data, not the positives in the predictions. And then we have true positive rate, which is also known as power or recall or sensitivity, which is the total number of positives, the true number of positives, which means that among those that were predicted positive, how many of them were truly positive. So we want the true positive rate to be as big as possible, and we want the false positive rate to be as small as possible. Or you can also say you like to have the specificity and the sensitivity to be as close as possible to 1. Let's look at extreme cases. You have the always one prediction Okay, let me correct something. The type 2 error is 1 minus the true positives divided by the positives. Which, if you, I mean, you could argue it's the false positives divided by the positives as well. But this is another way of writing it. And now let's look at this. yi is either 1 or 0, okay? So the sum of yi's is the total number of positives. Capital P standing for a total number of positives. So little n minus the positives, which is n minus the positive, is capital N standing here for the total number of negatives. And then we can just look at the proportion of positives in the data is just the sum of yi's, assuming yi is either 0 or 1, divided by the total number of observations we have. So simply we can write that positives is n pi hat and negatives is 1 minus pi hat times n. This will be useful in looking at some extreme cases. Now, imagine the always one prediction. The predictor that regardless of what the features are says always one. So the type 1 error in this case is the total number of false positives divided by the negatives. Well, since this is always 1, so the false positives will be the total number of negatives in the data. So the type 1 error will be n by n will be 1. Now the type 2 error, which is 1 minus the true positives divided by positives. Now the thing is that the true because this is always 1, not all of them are truly 1, but the true positives will be the total number of positives in the data, which this make this p. So p divided by p is 1, so 1 minus 1 is 0. So the type 1 error is 1, the type 2 error is 0. The other extreme is the always 0 prediction, in which case there will be no false positives, obviously, because there will be no positives to have them false. And then there will be also no true positives. So you have a type 1 error of 0 and a type 2 error of 1. Now in the middle ground, we have a predictor which randomly assigns the label 1 and 0 according to just flipping a coin, but the coin has a probability of pi hat, which pi hat is, just to remind you, is the proportion of positives in the data. Now, if the proportion of positives in the data is around 50%, as is the case in the IMDb example, classifying reviews into positive and negatives, then there won't be much of a difference because it's 50-50 anyway. This random assignment becomes important when you have unbalanced data. Now, the reason is, it will become clear in a second when we look at the type 1 error. So what is a type 1 error? Is the false positive divided by the negatives? Roughly speaking, the negatives is just, not roughly speaking, it's exactly, it's n times 1 minus pi hat. Now the false positives is, roughly speaking, it's this essentially. It's the number of observations so the false positives are all the observations, predictions such that the true observation response is 0 while the predicted one is 1. And since these two, this y hat is just assigned randomly 1 and 0, it's independent of whether yi is 0 or 1. So you can write the joint probability into the multiplication of these two probabilities, and then roughly speaking, the probability of yi being equal to 0 is just 1 minus pi hat, and this is pi hat just by definition. So the type 1 error is pi hat, and similarly you can show that the type 2 error is 1 minus pi hat. If you write this probability the same way we have written it here, you can show that the type 2 error is pi hat. And this plays a role when the data is unbalanced, because when it's unbalanced, then let's say pi hat is 90%, then you have a type 1 error of 90%, whereas you have a type 2 error of 1 minus 90%, which is 0.1%. So going from these extremes of 0, 1, 0, 1, we have to come a little bit to a middle ground, and this middle ground is just if we completely ignore everything that goes into the prediction regarding the predictors. So we disregard the predictors. Now, what do you do if you don't want to disregard them? That's the subject of of another lecture, in which I will go over an R code.